This is problem 7-38, and it's on page 270. For problem 38, design a roller chain drive. Specify the chain size, the sizes and number of teeth in the sprockets, and the number of chain pitches, and the center distance. So you'll notice the data is given on the row in the table above in table 713. It says that the driver type is an AC motor. The driven machine is a hammer mill. The input speed, which I'll call N1, is 310 RPM. The output speed, jumping over to the last column, is 160 RPM. Notice that it's been labeled as the nominal output speed because, again, we're going to choose a standard sprocket, right? You don't want to get just any sprocket. Even further, we're restricted even further in sprockets than we are in V-belts because the sprocket, you have to have an integer number of teeth. So we don't have too much of a choice there. And then the input power, they've got it in kilowatts and they have it in horsepower. I'll just write down both. Power is 25 horsepower, which is 18.6 kilowatts. That way if we need either one, we've got it. So we're supposed to figure out the chain size, so basically the pitch. This way. Given, find. What's the pitch? Sprockets, basically. The number of teeth on the sprocket would suffice there. Number of chain pitches. This is analogous to the length, okay? Because the more pitches you have, the more links you have, which makes more length of the chain. Hope all those words are clear on the video. And then the center distance. So that's what we're supposed to do is design this. Okay. The first thing I always do is find a service factor. So for the chains, go to page 263. And the type of driver is the label across the columns, and the rows are the driven machine or the load. Since we have an AC motor, then the electric motor would be my column of choice in the center. And the hammer mill, well, let's see. Hammer mills, notice under heavy shock, there's punch presses and hammer mills, etc. So what what service factor should I use for this? 1.5. It's at the intersection of those two. Okay, so the design power, piece of D, I guess, for design, although we use piece of D for something else later in the course. 25 horsepower, I think we'll probably end up using horsepower, so I'll just go ahead and go with it. I can modify, or I can later multiply 18.6 by 1.5 if we need it. So if you multiply 25 by 1.5, what do you get? Thank you, 37.5 horsepower. So we're going to design this drive as if it has to transmit 37.5 horsepower because we're going to abuse it a little bit. Okay? All right. Now, the next thing to do is to decide what chain we're going to use. Now, if you'll notice, go to page 260 and 262, and notice that these tables for the power capacity of the chains are based on the size of the chain. There's size 40, number 40, number 60, and number 80. Do you remember what those numbers mean? Well, that's just the pitch, right? 4/8 for 40 chain is a 1/2 inch pitch. So 60 is 3/4 pitch and 80 is 1 inch pitch chain. So those are the tables that we have. So obviously our selection is limited because of the data we have in the book. Okay. Now notice all of this works together. There's number of teeth for the rows and then the actual power that can be transmitted by the chain depends on the type of bath, the type of lubrication, I should say. So notice that all of these charts are separated into, or all these tables are separated into type A lubrication, type B in the center, and then type C on the right side. Okay? All right, so we have to decide all of this basically. So what shall we do? Well, there's a nice design guideline for chains on page 258 and 259. Now the V-belts didn't have such design guidelines, but since we have it here, we'll use it. Reading step 1 on page 258. The minimum number of teeth in a sprocket should be 17 unless the drive is operating at very low speed, under 100 RPM. Well, let's see, we've got 310 and 160, so I think we're okay. So we could use 17 teeth. Now, when I did this, what did I decide to do? I've forgotten. Let's see. I went a slightly different way. How about if we, I'll need calculator help, but this will probably involve you guys more. So let's go a different way. And let's see, minimum number of teeth should be 17. Could you choose less than 17? You're the designer. Yeah, sure you could. Is it a good idea to? Maybe, maybe not. Notice that in the tables, table 7.7 through 7.9, there's data listed for sprockets with less than 17 teeth. So we could go with that. But since it's a recommendation in these guidelines, I'll just go with 17 teeth for the smaller sprocket. So basically the number of teeth on the smaller, now the smaller sprocket is going to be the sprocket that's moving faster, right? That's going to be on 1. Now you have to be careful here. A lowercase n is for the speed in RPM, and uppercase n is a count of the number of teeth on the sprocket. Okay? So I'm just going to choose 17. Now if we want the output speed to be 160, shouldn't we calculate how many teeth we need? So let's do that next. So let's see, let me think for a minute. We're going to have more teeth. Let's see, let me just figure it out. Let's see, so this is going to be a number less than 1, so I need N2 over N1. You can go back in the slides if you want and find the equations, because I've got all the equations you need for this. But I can just figure it out, right? Because look, 17 is the lower number. I know I'm going to have more teeth for the slower speed shaft. So I need a ratio less than 1, and so I just plug in the RPMs in the correct places to get it. Okay, so my question was, what's N2? Well, from this I can figure it out. N1 over N2. So the speed ratio should be the number of teeth on the larger sprocket, the slower shaft. So anyway, 17 times 310 over 160. Grab your calculator, please, and tell me how many teeth we have. 33. Did it come out to an even 33, or did you have to round it off? 32.9. How much? 32.9. 32.9. Okay, so I agree that we could go with 33. However, what I would choose instead is 34. And the reason I would do that is because I'd like, well, maybe. It may be better to go with 33. We have an odd number of teeth on both. Yeah, let's just go with 33. That's fine. Let me think for a second. If we have an odd number of teeth on both, would that mean that the same length impacts the same tooth? I'd have to think about it. I don't think it does, because this ratio is not integer. So, yeah, so we should distribute the wear between the chain and the sprocket. Does that make sense? Okay, so I just wanted to make sure. For example, I wouldn't want to go with 34. Does that make sense? Because then the same tooth on the sprocket is going to be worn by the same link on the chain over and over again. I don't want that to happen. So it seems like this would spread it out well. Now, reason for not going with an integer number of teeth on the sprocket is, again, or an even number on the sprocket is to, again, spread out the wear. So this should work fine. All right, so there's the number of teeth on the sprockets. That takes care of that. We still haven't decided on the pitch, or the number of pitches, but let's continue with the guideline. Maximum speed ratio should be 7, although higher ratios are feasible. You can see that's about 2 to 1. Two or more stages of reduction can be used to achieve higher ratios. We don't have to worry about that. The center distance between the sprocket axes should be approximately 30 to 50 pitches. So 30 to 50 times the pitch of the chain. And so far your author hasn't gone through a critical step. We have not actually selected the chain yet. So let's go do that. I don't know why he doesn't have that in the list. But let's go into the tables and use this 37.5 horsepower to select the chain. Now notice that the horizontal axis of these tables essentially is based on the rotational speed of the smaller sprocket. So that's the 310 RPM. Now let's see, in number 40 chain and number 60 and, if I remember right, number 80 chain, that would constrain us, since we're at 310 RPM, to have type B lubrication. So let's go ahead and write that down. Do you notice how 310 RPM lands us in the center of these charts? Okay, so we're going to specify at this point that we will definitely need bath or disc lubrication. All these things are important. We're trying to design it, right? We want to make sure it works. Now, the number of teeth we chose was 17. And if we look at the row for 17 teeth and go over to 310, we could interpolate, and if it's bad enough, we might have to. But 310 is so close to 300, I think I would just read it off of the chart. Notice we have a small problem. How much horsepower can one chain strand take at 300 RPM and 17 teeth? 2.29. How much do we need? Over 10 times that. This would take over 10 chains to do it. Let's move up in chain size and see what happens. 17 teeth at 310 RPM at roughly 300. Well, we can take about 7.5 or so horsepower, right? That's better. Still not good enough. Let's move up again. 17 teeth, number 80 chain, 300 RPM. Now we're talking 17.86 horsepower. Another option is to increase the number of teeth. Notice we chose 17. We could increase the number of teeth, but notice that increasing the number of teeth doesn't really increase the horsepower near as quickly as changing the chain size. And it's important when you're solving these problems to have a feel for what parameters will affect the design the most. The chain size in this case is a huge piece of that, which makes sense. All right, so 17.86 horsepower. 17.86. We could interpolate and bump that number up a little bit, but I think if we multiply this by, let's see, what do we need? 2 at least? It'd give us, what, 38 horsepower? Yeah. So if we choose 2 strands, then everything's good, right? Wrong. Let me show you why. There's a little bit of information about chain you need. Go back to page 258, and this is not in the design guidelines. You have to be really careful about this. On page 258, you see item 4 in the right-hand column? You notice there's 3 equations. It says 2-strand factor equals 1.7, 3-strand factor equals 2.5. You'll want to highlight that. That's really important. Basically what that's saying is that when you add a chain, you do not double the capacity. The factor is 1.7. So you have 2 chains, then the amount of power that those 2 chains can take together is 1.7 times this, not 2 times this. Okay? That doesn't seem fair. Why is it? Well, the chains, if you stop and think about it, the rollers on the 2 chains are never going to be exactly in sync with each other. Does that make sense? Because of manufacturing variations, they're going to be slightly different size. They're going to be one sitting back slightly from the other. And that's going to dramatically affect the contact between a tooth of the sprocket and the roller itself, or the bushing. Does that make sense? And so one chain is always going to take more load than the other, or as it moves along, as you get these different links along the chain impacting the sprocket, one's going to take more load than the other. And that's what this factor is for. Does that make sense? Any questions on that? Okay, so multiply this by 1.7 and let's see if 2 strands will work. What is 17.86 times 1.7? The answer is not enough, right? Okay, so what about 3 strands? Well, with 3 strands, the factor is 2.5. So 2.5 times 17.86. Will that work? Okay, so how much power can we actually transmit if we have 3 strands?
45.
45?
Yeah.
All right, so that should get us there. So far what we've discovered is if we're going to go with these sprockets, we will have to have 1 inch or number 80 chain, and we need 3 strand. Okay? All right, are we done? Not quite. We still need to know how long the chain is. So we need the center distance between and the number of pitches. Okay, let's read more of the guidelines. Step 4. Oh, here we go. Center distance between the sprocket axes should be approximately 30 to 40. I'll just choose, or 30 to 50. I'll just choose 40 since we're running out of time here. I think we're done with this part. So I'll say center distance C is 40 pitches, just because it's halfway in between what's recommended. Let's see, the larger sprocket should normally have no more than 120 teeth. That's fine, ours does not. The preferred arrangement for a chain drive is with the center line of the sprockets horizontal and with the tight side on top, okay. Chain length must be an integral multiple of the pitch, and an even number of pitches is recommended. The center distance should be made adjustable to accommodate the chain length and take up any tolerances and wear. Excessive sag on the slack side should be avoided, especially on drives that are not horizontal. The convenient relation between center distance C and chain length L, number of teeth in the small sprocket N1 and number of teeth in the larger sprocket N2 expressed in pitches is, finally we get to the equation 7 and 9. So the length in pitches, which is what we're going for, is 2 times the center distance in pitches again, plus the sum of the number of teeth on the sprockets over 2, plus the difference in the number of teeth on the sprockets squared over 4 pi squared C. Okay? Remember, this is our target. This is what we're shooting for, but we can't guarantee that the actual center distance between the 2 sprockets will be exactly 40 pitches, right? So this is what we have to use instead. So 2 times 40, I'll just do some of the math for you, that's 80. Plus N1 plus N2, that's the sum of these two. We can all do that in our heads, right? That's 50. Over 2 is 25, so there's the next term. Plus, now this one I can't work in my head. N2 minus N1, 33 less 17. That's, what, let me think. 13 plus 3 is 16. So 16 squared, now I do know 16 squared, that's 256. I might be in trouble there, I might be wrong. Over 4 pi squared times the center distance, which is 40. Is 16 squared 256? Did I get that right?
Yeah.
Okay. All right. So I'm just trying to calculate as much of this as I can to save time. Okay. So please give me a number here because I can't divide by pi squared in my head very well. Not quite there yet. Why not? Come on.
105.16.
105.16. Okay. So they recommend an even number of pitches for the chain. That was in step 6. All right. So now, if we know the actual number of pitches, let's see, then we know the length of the chain. Notice in the next equation, 710, this is analogous to what we did with the belts, right? We said we want about this much center distance. Okay, choose a standard length V belt. Now what's the actual center distance? That's what we're doing with 710. So let's see, this is all on the video, so I guess I can erase this part. I don't want to erase this because this is a specification. All right, so the actual center distance, oh, we haven't selected it. So let's select an even number. What do you want? Now, you're probably going to say 106 or 104. And I'm trying to break that. That's thermo, that's dynamics, that's hardcore calculation classes. Here we're designing. Let's choose 100. Okay, it's an even number. It's reasonably close. Could you choose 80? Probably. In fact, why don't we try it? Let's be engineering rebels. We're gonna design them the way we want to, by golly, right? Let's choose 80. Let's see what happens. Because as long as we end up between 30 and 50 chain pitches, it's a valid design, right? According to our guidelines. So now, equation 710. Center distance is 1/4 of L. Now, L is the actual number of pitches that we're choosing for the chain length. That's 8. Less N2 plus N1, I'm going to fill in numbers. You should follow along on page 259. N2 plus N1 is the number of teeth added together. We've already discovered that that's 50, which divided by 2 is 25, so that's the next term in the brackets, plus the square root of L, which is the length of the chain again, 80, minus, same thing, 25, quantity squared, less 8 times the square of the difference between the two, so we figured out that was 16, which when squared is 256, so again I'll make the substitution for you, 256 divided by 4 pi squared. Okay, whoops, do you guys see where I got all these numbers from? I'm just doing some of the math in my head as I plug it in. Oh, I need to end that. So please plug this into your calculator. I see questioning looks. Any questions about where I got anything? Since there's dead space, I'll describe it. This number came from N2 less N1 squared, so 16 squared is again 256. This is the same as here, it's the length in pitches. These numbers here are N1 plus N2 over 2, so that's 50 over 2, which is 25. And the 8 to 4, and the pi squared came from the equation. Now, why they've got an 8 here and a 4 here, I just noticed that really they could have just done that. Right? So the 8 and the 4 simplify. Never thought about that before. And I know what that is, that's 512.
Square.
Well, we've already squared it, right? Because I had the 256. Anyone have a number?
27.38.
27.38. So I shot myself in the foot, right? Because I should have 30, so I went a little too far. But you see the principle of how this works, okay? So maybe I should have chosen 100 or 90 or something. Okay. Now there's a little bit more information. There's the pitch diameter of the sprocket in equation 711 that you can calculate. This just tells you how big the sprocket is. Because notice we didn't specify that. We specified the number of teeth, but not the diameter. The diameter is going to depend on what chain pitch you choose. And then the wrap angles, equations 712 and 713 are important because you want to make sure the chain wraps around the sprocket enough to actually transmit power. I don't know if you guys have ever had the bicycle that you left outside in the rain on accident, and you got on it to ride it, and as you're pedaling the chain pops. Well, part of the reason it does that is because the links rust a little bit and it's more difficult for them to wrap around a tighter angle quickly. And so also if you look at the rear sprocket on a bicycle, like a 10-speed or whatever speed you got, the wrap angle is only about 90 degrees. It's a little more than that, but it's certainly not 180 degrees. And so that can cause, well, it's not 90, it's more than that. But still, it's certainly not 180 degrees. I wish that the derailleur was designed so the chain actually came around and had more than 180 degree wrap angle, because then it would be a little more reliable. Questions, comments? All right. Well, have a good evening, guys.